Hi everyone, welcome back to Chapter 9. This is Lecture 2 and this will be the last lecture of Chapter 9. And before we pick up where we left off, I thought it would be a good idea just to give you a very quick review. And of course in Chapter 9 we started talking about one-way or single factor ANOVAs, and these are statistics that are used to analyze one independent variable with 3 or more levels. We talked about how it would be inappropriate just to keep using t-tests and compare means 2 at a time, because that would inflate what? Your overall risk of a type 1 error. And that I gave different names for it, but we'll just call it the experiment-wise alpha. All right, so ANOVAs are great because if you set your alpha to be 0.05, it doesn't matter how many means are being compared, the risk of a type 1 error will not exceed 0.05. So that makes the ANOVAs the preferred statistical method for analyzing data like this. All right, we also talked about the F value or the F ratio. And I explained how all F values divide one variance by another variance. And in the case of ANOVAs, the F value takes between group variability and divides by within group variability. The within group variability is your error variance. You can think of this as your error term. You can also think of this as the background noise that your treatment effect has to get above in order to be seen or heard. So it's like it's in some ways like a baseline amount of noise. And that goes here in the denominator. And if we look more closely, within group variability is looking at the variability of scores within each group separately. And then it's giving you a combined or a pooled variance estimate, which is basically just a mean of these 3 estimates of variability. And we said that the only way or the only thing that could explain why these scores are variable within a group is individual differences in error. It can't be due to a treatment effect because they all were in the same group, right? The same level of the independent variable. The same is true here and here. So it's like we're getting 3 independent estimates of how much scores should vary just because of individual differences and error. And then what we do is, like I said, we combine them so we get a pooled variance, and that's within group variability. The between group variability looks at how the means vary. All right, so we're going to calculate the variability between these means. And that is where we might see a treatment effect, because these means could differ because of individual differences in error. After all, each mean is made up of a different group of people. And it also could be error, right? We're always going to have error. But these means differ in another respect, and that is they represent different levels of the independent variable. So that opens up the possibility that maybe the means are different just because of individual differences in error, but they might also be different because of a treatment effect. In other words, maybe the independent variable matters. If treatment effects are in fact 0, then you're going to have individual differences divided by individual differences. Oh, and error. Let me sneak that one in. But essentially, you're having one number dividing by a very similar number, you're going to get an F value very close to 1. And that's not going to be significant. In essence, it's telling you that your means varied about the same amount as individual scores where there was no treatment effect. So if your means are varying to the same extent as your individual scores, then that tells you that you probably have null, not a nothing. However, if we find that the means vary far more than the individual scores within each group, then that's saying something is probably going on, something above individual differences in error. In other words, we probably have a treatment effect. Now, when you get a significant F value, all that tells you is that there is a difference somewhere among your means, but it doesn't tell you where those differences are. And that's where we introduced the post hoc tests. I gave you a little bit of a surprise quiz here. We said post hoc tests are not needed for significant t-tests, and that's because t-tests are only comparing two means. So if your t-test is significant, then the difference has to be between those two means. There's no other possibility. But when you do an ANOVA, you have 3 or more means. You should ignore this. I popped that up prematurely. When you do an ANOVA, you have 3 or more means. Pretend that each letter is a mean here, all right? And you found out your ANOVA is significant. Well, how do you know which mean is different from which, right? There's so many different possibilities. And that's why we do what's called post hoc tests.